part 1 of this lesson, I taught you how to find the intersection of two planes. And we learned that two planes, if they intersect, are going to intersect in a line. What we're going to do in the second part of this lesson is look at how can three planes intersect. And we'll start this part of the lesson off by looking at the consistent solutions we could have when we have a system of three planes. Three planes could have a single set of xyz values that satisfy all three equations, and graphically how that would show up is that the three planes would intersect at a single point. Or the three planes could have a line of points that satisfy all three equations, and graphically we would see that all three planes intersect in the same line. Or I suppose all three planes could be the exact same plane, meaning that every single point on each of the planes satisfies all three equations, so we would just say there are an infinite number of solutions. So let's go through a couple of examples so that you're able to find these intersections when we have a system of three planes. Example 2 says, for each set of planes, describe the number of solutions and how the planes intersect. And notice that we have three planes here. So we're trying to see, is there an xyz value or multiple sets of xyz values that satisfy all three equations? What we're always going to do for this is we're going to start by picking a pair of planes and then see how does that pair intersect. And then we'll pick a different pair of planes and we'll see how does that pair intersect. And then we'll compare those intersections to see if there's a consistent solution between all three planes. The first pair of planes I'm going to pick to start with are planes 1 and 2. I'm going to try and figure out how do plane 1 and plane 2 intersect. What we always do to start off with is we try to eliminate one of those three variables that the equations have by using the method of elimination. So I'll start by stacking the two equations on top of each other. And my goal is to eliminate a variable. So I'm going to need the coefficients of either the x's, the y's, or the z's to be the same so that I can either add or subtract the equations to eliminate a variable. How about I eliminate the z's? In order for the z's to eliminate, I need the z of equation 2 to have a coefficient of 6, so I'm going to multiply it by 2. So let me just go ahead and multiply all the terms of equation 2 by 2. And now because the coefficients are both positive 6, they're the same sign, I know subtracting will eliminate the variables. So I will subtract all of the like terms. When I subtract the x's, I get negative 4x. When I subtract the y's, I get negative 7y. The z's will eliminate. And when I subtract the constant terms, I get 23, right? 7 minus negative 16 is 23. When I eliminate a variable, I was left with two variables. So that tells me that plane 1 and plane 2 are going to intersect in a line. Before I go ahead and actually find the equation of that line they intersect in, I'm instead going to now pick a different pair of planes, either planes 1 and 3 or 2 and 3, and try and figure out how do those two planes intersect. So I'm going to choose planes 2 and 3 this time, so I'll stack those equations on top of each other. And now we need to eliminate a variable with those two planes. Now the key thing here, I need to eliminate the same variable that I eliminated with planes 1 and plane 2. So I need to eliminate the z again. So I'm going to make the coefficients of both of those z's, I'm going to make them be 12 and negative 12. So I'll multiply equation 2 by 4 and equation 3 by 3. So let me go ahead and adjust all of those coefficients. And now because the coefficients of the z's have the same absolute value but opposite signs, I know that adding them will eliminate them. So I'll add all of the like terms. That will give me 15x plus 10y plus 0z equals negative 5. And let me actually simplify this equation by dividing all of the terms by 5, which will give me 3x plus 2y equals negative 1. So I've created two new equations. I'll call them equation 4 and equation 5. Those equations tell me that each pair of planes that I worked with both intersect in lines. Now if we go back to the diagrams of what the possibilities are, the lines that I just found are either the same line, which means all three planes intersect in the same line, or those two lines I found are different lines, meaning that the three planes are going to intersect at a single point where those two lines that I found intersect. So let's go ahead and try and see how do those two lines I found, here and here, equation 4 and 5, How do they relate to each other? Let's try eliminating a variable with those two equations. So I'll stack equation 4 and 5 on top of each other. And let's eliminate the x's. We could eliminate the y's, doesn't matter. To eliminate the x's, I'll make their coefficients be negative 12 and 12. So I'll multiply equation 4 by 3 and equation 5 by 4. And let me adjust the coefficients of each of those terms. And because the coefficients of the x's have opposite signs, I know adding will eliminate the variables. So let me add all the like terms together. I get 0x, the x's eliminate, minus 13y equals 65. The fact that I still have a variable remaining tells me that these two lines actually do intersect. So I know that if we look back to the diagram here, I know that the lines I found between the different pairs of planes, like let's say we were working with the blue and the red first, we found they intersect in a line. And then we looked at the green and the blue, they intersected in a line. Now what we have just figured out is that those two lines actually intersect at a point. And what we're doing now is we're finding the coordinates of that point. We can find the coordinates just by continuing to solve. We can divide the negative 13 to the other side. 65 divided by negative 13 is negative 5. And now let's continue finding the x and z value of this single point that satisfies all three equations. So I can take this y value of negative 5 and sub it back into equation 4 or 5, the multiplied version or the original versions, it wouldn't matter. Let's sub y equals negative 5 into equation 5. And now I can go ahead and solve for x. So I have 3x minus 10 equals negative 1. 3x equals 9. X is 3. So when x is 3 and y is negative 5, all three planes are at the same point. But what is the z coordinate of that point? I can now take these x and y values that I've solved for and sub it into any of the three original equations. It wouldn't matter which of the planes we sub it into, because all three planes are at the exact same point at these x and y values. So let's make a note of what we're doing last. We will sub x equals 3 and y equals negative 5 into equation 1 or 2 or 3. I'll sub it into equation 1. Equation 1, I think, was 2x plus y plus 6z equals 7. Let me just double check that. Yeah. So if I sub in those x and y values and go ahead and solve for z, I have 6 minus 5 is 1. Move it over. 7 minus 1 is 6. Divide the 6. I have z equals 1. So I can say the point of intersection of the three planes is the point 3, negative 5, 1. That is the single set of x, y, z values that would satisfy all three equations. And of course, in any algebraic solution, we could go ahead and check and make sure that this solution is correct by subbing in those x, y, and z values into all three equations of the planes and doing a quick left side, right side check, making sure it satisfies all three of them. Let me also show you what this system looks like in Desmos, and hopefully it'll help you understand better what we did here throughout this algebraic process. All right, here we go. Here's the system of planes that we worked with. Notice that the three planes all intersect at this point A. This point A is on all three planes. What we did is we first algebraically looked at the red and green planes, and we saw that they intersected in a line. We then looked at the green and blue planes and saw that they intersect in a line, and then we found where those lines intersect, and that must be where the three planes intersect. All right, let's move on to part B. So in part A, the three planes all intersected at a single point. In this one, we're going to have a different scenario, but the process to start is going to be the same. We're going to look at two different pairs of planes, and then compare the intersections of those two different pairs. So let's start by looking at plane 4 and plane 5. I see that both the z's and the x's would eliminate very easily, but let's just go ahead and stack those equations on top of each other to start with. And since both the x's and the z's, their coefficients have the same absolute value, I could eliminate either. I'm going to choose to eliminate the z's. So I will be adding the two equations to eliminate the z's. And when I add all the like terms, I would have 2x plus 2y plus 0z, the z's eliminate, equals 10 plus negative 6, is 4. And I could simplify this equation a little bit. If I wanted to divide all of the terms by 2, I would have x plus y equals 2. So I will call this equation 7. I'll be working with that later. And now let's go ahead and look at a different pair of planes, either planes 4 and 6 or 5 and 6. I'll choose to do 5 and 6. So I'll rewrite equation 5 and 6 on top of each other. And remember, when I choose to eliminate a variable in my second pair, I have to eliminate the same variable that I did in my first pair. So I once again have to eliminate the z's. So I will need to make the coefficient of the z in equation 6 the same as the one in equation 5. So I'm going to multiply it by 2. Let me multiply all of the terms by 2. And now I can go ahead and add these two equations together to eliminate the z variable. That would give me 17x plus 17y, the z's eliminate, equals 34. And once again, I could divide this equation by 17 to simplify it, and that would give me x plus y equals 2. And I'll call this equation 8. And what do you notice about equation 7 and equation 8? Notice they're the exact same equation. So that tells me that the line of intersection in each pair is the same. Now, if you didn't notice that, or maybe if you didn't simplify the equations like I had there, you would go ahead and try and eliminate a variable between equation 7 and 8. And if you did that, what will happen? When you will try and eliminate a variable, if we subtract the two equations, I get 0 equals 0. That tells me that the two lines that I have, the line of intersection of equation 4 and 5 and the line of intersection of equation 5 and 6, is in fact the same line of intersection. That means all three planes must intersect in the same line. So if we go back up to this diagram from the beginning of the lesson here, we found, let's say, that green and red intersect in this line, and blue and red intersect in this line, which means all three planes must intersect in that same line. So now what we have to do is find the equation of that line. So this is the line of intersection, but we can't have a scalar equation of a line in 3 space. That refers to a plane, so we need to find the vector or parametric equations of this line. I taught you how to do that in the previous video for part 1 of this lesson, but I'll quickly take you through how to do that again here. When we're finding a line of intersection, after we've eliminated one of the variables, like we already have in this version of the equation, the z's have already been eliminated. When we're left with our two variables, we get to choose one of those two variables to be our free variable. We get to set it equal to just t. And then remember, when we write the parametric equations of a line, we want to write all the variables in terms of the parameter t. So we get to pick either the x or the y, either of the remaining variables, to be equal to t. Let's say let x equal t. And now we have to try and write y and z in terms of t as well. So we can take that equation that we just had right here, x plus y equals 2, and we can replace the x to t. So it would be t plus y equals 2, and then isolate y would equal 2 minus t. So what we have, if we're trying to write the parametric equations of the line, and I'll have it flash on the screen for you here what the parametric equations typically look like, we now have what x is equal to in terms of t and what y is equal to in terms of t. The last thing we need is what is z equal to in terms of t. And we can calculate that by summing our x and y parameters into any of the 3 original equations. It wouldn't matter which one we do. The numbers in equation 4 look the smallest, so I'll sub into that. Let me just make sure I wrote that equation right. X minus 5y plus 2z equals 10. Good. So let me change the x to t. Let me change the y to 2 minus t. And I have to now isolate for z. So I have t minus 10 plus 5t plus 2z equals 10. So I have 6t. And I'll move the negative 10 over to give me 20 on the right. I'll then subtract the 6t to the other side, 20 minus 6t, and then lastly divide the 2. I have 10 minus 3t. So I have the parametric equations of the line. Let me go ahead and write them. So I'll say the line of intersection is, and now I'll sub in my parametric equations. X was equal to t y was equal to 2 minus t, and z was equal to 10 minus 3t. So we could leave the parametric equations like that, or we could write the vector equation where we write the vector x, y, z is equal to a sum of the position vector, which we get from the constant terms, which were 0. We set that. Then 2 and 10, plus a scalar multiple, we call it t, of the direction vector, which are the coefficients of t, which are 1, -1, and -3. So either of those final answers describe the line of intersection. So any point that falls on that line satisfies the equation of all three planes. And now let's go over to GeoGebra so you can see the situation we had. So here are the three planes we are working with. We started off by finding how do the red and the green plane intersect, and we figured out that the red and the green plane intersect in this black line of intersection. And then we looked at the green and the blue plane and figured out they intersect in the exact same line of intersection. So that means that all three planes share a line of intersection, and we calculated the equation of that line of intersection and said that is the consistent solution for our system. Let's now look at what's going to happen if we don't have a consistent solution for all three planes. I have a diagram of a few things that could happen. There are more scenarios, but these are some common ones you may run into. We could have a pair of planes in our system that are parallel. Notice that the purple plane and the blue plane here are parallel. And how can we know that from the equations that they're parallel? If you remember back to our previous lesson, if two planes are parallel, their normal vectors, let me just sketch the normal to both of these, their normal vectors would be parallel to each other, meaning the normals are scalar multiples of each other. So you may notice right away that two of your planes are parallel, and you could figure out they're parallel and distinct algebraically. And that would tell you right away, if two planes never cross, then there's no way all three planes can share a point or line of points of intersection. So if you have two planes in your system that are parallel and distinct, like the purple and the green in that diagram there, then you know there is no consistent solution in your system. But if we look at the middle scenario, this one is the trickiest because when you look at your first pair, let's say you look at the green and the red first, you'll find that they have a line of intersection. And then let's say you look at the red and the blue next, you'll notice that they have a line of intersection. But those two lines that you find, those two lines are never going to cross, which means that the planes are not going to share a point of intersection. So what we could have are three planes where each pair intersects in different lines, but those three lines never actually meet, which means those three planes will never converge on a point that they share. So there would be no consistent solution in that system either. And in the third diagram here, I just showed you a system where all three planes are parallel and distinct. So let's look at a few examples here. Some of them will be able to know very quickly that there's no consistent solution, and others will have to do a bit of algebra. Like if I look at example A, I may want to just look at the normals very quickly, and specifically the normal vectors from plane 1 and plane 3. And remember, the normal vectors are the coefficients of x, y, and z when we have the scalar equation of a plane. So the normal vector for plane 1, I'll call it normal 1, is equal to 3, 1, -2. And the normal for plane 2 is equal to 12, 4, -8. If you notice, those two normals are scalar multiples of each other. If I were to multiply normal 1 by 4, so 4 times normal 1, it would be equal to normal 2. That means that the normals are parallel to each other, which means that the planes must be parallel to each other. Now, are those planes parallel and coincident? Maybe they're the exact same plane. Or are they parallel and distinct? There's a couple ways we could check that. We could check if it's the same scale factor or same ratio between the constant terms. Or we could go ahead and try and eliminate a variable with those two planes and see what happens. And I'll just show you that. So if I were to try and eliminate the x's between plane 1 and plane 3, I'd have to multiply plane 1 by 4. And that's going to actually make all of the coefficients of the variables the same. And if I were to subtract these two equations from each other, everything on the left eliminates, so I'd have 0, equals, and on the right I have 52. Well, 0 can't be equal to 52, so that tells me that plane 1 and plane 3 are parallel and distinct. And if two planes in your system are parallel and distinct, there's no consistent solution for your three planes. It doesn't matter what plane 2 is. Maybe planes 1 and 2 and 2 and 3 do intersect in lines, but I know those two lines are never going to converge on each other because plane 1 and plane 3 are parallel and distinct from each other. So let me just go ahead and write out that answer. There's no consistent solution, and I've described how I know that. That's because there's a pair of parallel and distinct planes in our system. And now let me show you in GeoGebra what we had in this system. Notice here's plane 1 and plane 3. We figured out they're parallel and distinct. We didn't even analyze plane 2. If we had just looked at plane 1 and plane 2 first, we would have seen they intersect in a line. And then if we had have looked at plane 2 and plane 3, we would have seen they also intersect in a line. But because 1 and 3 are parallel and distinct from each other, those two lines of intersection will of course never cross, so we have no consistent solution. Let's move on to part B, where we might have to do a bit more work for this one to see if there's a consistent solution or not. I could start by looking at the normal vectors. Let me just jot them out here and we can look at them quickly. So if I look at all three normal vectors, if I look at the different pairs I could make, 1 and 2, 2 and 3, or 1 and 3, none of those pairs are scalar multiples of each other, which means none of the normals are parallel to each other, which means none of the planes are parallel. So that tells me we have one of a few scenarios. If none of the planes are parallel, it could mean that we have this scenario here where they intersect in different pairs of lines, but those lines never intersect. Or it could be one of our earlier scenarios where we have a point of intersection or a line of intersection. So we're going to have to start trying to solve and just see what happens. The process is going to be looking at two different pairs of planes and eliminate the same variable from each pair. So maybe let's eliminate the x's. Let's do it let's pair up 4 and 5 and 4 and 6. So let me write 4 and 5 on top of each other. And I said I wanted to eliminate the x, so I'm going to have to multiply equation 4 by 2. So let me just double all of the coefficients of those terms. And now let me subtract the equations so that I can get the x's to eliminate. The x's eliminate. 6y minus y is 5y minus 3z equals negative 28. So I have two variables left here. This tells me that planes 4 and 5 do intersect in a line. Now I want to look at how does another pair of the planes in this system intersect? Do they also intersect in a line? So I said I was going to choose 4 and 6 this time. And remember, the important thing is we are eliminating the same variable that we eliminated in the first pair. So I'm going to eliminate the x again by subtracting. And that gives me 5y minus 3z equals negative 10 minus negative 4 is negative 6. So I have two new equations here. I'm going to call them equation 7 and equation 8. And these equations that I got by eliminating the variables show me that each of these pairs of planes intersect in a line. But how do these lines of intersection compare? Notice if I were to try and solve the system of these two new equations by using the method of elimination, let me stack the equations on top of each other. If I were to try and eliminate a variable, I could subtract the equations. Notice both the variables would eliminate. I'd be left with nothing on the left, but on the right, I'd be left with negative 22. My equation says 0 equals negative 22, which is not possible, which means that these two lines of intersection are lines that are parallel to each other but distinct from each other, which means they would never intersect. So the system that I have is this one here. I found these two lines of intersection, and I figured out that those lines never meet with each other. Therefore, the system of three planes has no consistent solution. No consistent solution. The planes intersect in pairs. And now let me show you once again in GeoGebra what we found here. Here are the three planes we worked with. Notice that the three planes, like we figured out, are not parallel to each other. But more importantly, what we did was we looked at the red and the green first, and we saw that they intersect in a line. And then we also looked at the red and the blue and saw they intersect in a line, and we figured out that those lines never intersect. Therefore, the three planes never converge on a single point, so there is no consistent solution for that system. And here is our last system we're going to work with. We could compare the normals right away and notice that the normals are all scalar multiples of each other, which tells us all three planes are parallel. But the ratio between the constant terms don't share that same ratio, so all three planes are parallel and distinct. But let me just show you algebraically, if you didn't notice that, what would happen and how that would tell you that what you have is in fact an inconsistent system. So let's say we wanted to work with planes 7 and 8 first. Let's say we wanted to eliminate the x's and we wanted the coefficients of the x's to be 20 and negative 20. I could multiply equation 7 by 5 and equation 8 by 2. Let me go ahead and do that and change all of their coefficients. And now let me multiply equation 8 by 2. And if I were to add these equations to eliminate the x's, I would notice that all the variables eliminate. And on the right, I would be left with 215. I have 0 equals 215. That tells me that plane 7 and plane 8 are parallel and distinct. Now, that's enough right there to tell me that we have an inconsistent system. Because if two of the planes never intersect at all, of course, all three planes couldn't share a point or a line of intersection. So we could stop right there. If you were to complete this process with another pair of planes in this question, either planes 7 and 9 or 8 and 9, you would find the same thing happens. And that would then tell you that all three planes are parallel and distinct from each other. So I'll just conclude with that. I'll say it's an inconsistent system or no consistent solution. The planes are parallel and distinct. So that's actually the very end of the vectors portion of this course. For these types of questions, make sure you definitely try the practice problems. You can get them from jensenmath.ca. Find this corresponding section there, try out the practice problems, and you can always check your solutions there as well. Jensen Math.